So what we're going to do is we're going to start out looking at trig integrals, and we're going to be utilizing some trig identities in order to do substitutions. So here's a list of the important trig identities that we're going to be using quite a lot of inside of this particular lesson. Okay, you'll notice over here that we've got our Pythagorean identities. All right, sine squared x is 1 minus cosine squared x, etc. And then we have some other identities, cosine squared x being 1 half plus 1 half cosine 2x, and this is one of the ones that we're going to be using in order to make to allow us to do some U substitution. Same with the sine squared x. And then the other piece that we're going to need, because what we're basically going to be doing is U substitutions, is you're going to want to make sure that you know what all of the derivatives are for your trig integrals, your basic trig integrals. So make sure that you have those written down because they're going to become very handy. So let's take a look at this example. We've got sine squared r cosine cubed r dr. And what I want to do here is, or what I'm going to do is, I'm going to be thinking about this problem in terms of those identities and also what I'm going to be doing for U substitution. So what I want to do is, if I can pull out either a cosine or a sine, right? Okay, so either I'm going to pull out a sine or a cosine, all right, and then get everything else written in terms of the other trig function, then what I can do is I can do a direct U substitution, right? And because I will have the appropriate du, all right, I'll end up having the appropriate du, all right? And so a lot of that's going to have to do with the powers of each one of the functions. So if I think about this, if I separate out, okay, so I'm just going to put a little note over here. I'm going to separate out cosine cubed r, and I'm going to make it cosine squared r times cosine r. And if I do that, what I get is I can substitute or transform this into 1 minus sine squared r, okay, cosine r. And if I have that, what I'm going to end up having is I'm going to end up having, this is my du, and then everything else is going to be in terms of sine. All right, and what that'll allow me to do then is allow me to do a U substitution, which is the whole point of what we're doing here in the trig integral stuff. So I got equals, and so I'm going to do that. I've got the integral sine squared r, and this will be cosine squared r cosine r dr. And that'll end up equaling the integral of sine squared r times 1 minus cosine, 1 minus sine squared r, and that's my substitution, times cosine r dr. And then just doing a little algebra, I'm going to get sine squared r minus sine to the fourth r times cosine r dr. Okay? So if what I do is, if I let now I'm going to do my U substitution, because I can let u equal sine r, and thus du is going to equal cosine r dr, which is exactly what I want to have happen, okay? Because now what I have is this is going to equal the integral, and it'll be u squared minus u to the fourth du. And that's a simple integral for us to go out and integrate. Okay, this will end up being 1/3 u cubed minus 1/5 u to the fifth plus c. And when we resubstitute back in, we end up with 1/3 sine cubed r minus 1/5 sine to the fifth r plus c. And that is the solution to our trig integral. Okay? So the idea here is, if we notice, we have an odd number of cosines. And since I have an odd number of cosines, I can pull out one of the cosines, okay? And I'm left with an even number of cosines, which can be replaced for 1 minus sine squared r, or some power of 1 minus sine squared r. This is also true because sine is also to an even power, right? So consequently, we don't have to worry about, well, actually, that's all. That's really what we want. We want to make sure that our cosines to some odd power, we can pull out a cosine and then left with some way to substitute 1 minus sine squared r, or a power of 1 minus sine squared r. So let's take a look at a different example. This time we're going to use secant and tangent. So what we want to do is we want to remember what those derivatives are for both secant and tangent. I hope you wrote them down. And also remember that we're going to want even powers for both secant and tangent. Okay? So what I'm going to notice about or what I'm going to think about is that if I actually pull out just a tangent, so if I pull out a tangent, x, like I did previously with the cosine, I'm going to be left with secant to the ninth x tangent squared x times tangent x, okay? But tangent x is not a derivative of secant. The derivative of secant is secant x tan x. So consequently, that's not going to help us out too much, okay? So we don't want to do that. If I, on the other hand, I also pull out secant squared x, right, which I do know is actually the derivative of tangent x, right? Then I end up with secant to the seventh x tangent cubed x dx. But then what I notice here is I can't substitute, or I can't fully substitute. I'm going to actually end up with an extra secant instead of having just tangents. And since I end up with an extra secant instead of having just tangents, I don't want to do that either. On the other hand, if I pull out a secant x and a tan x, okay, so let's say I pull out secant x and tan x. So I pull out secant x tan x. What I'm left with is I'm going to be left with secant to the 8x tangent squared x times secant x tan x. And so when I substitute, what I can do is I can substitute in for secant x and utilize my secant x tan x dx as my derivative. Okay, so that's what I'm going to do. Right? It makes sense to utilize secant x tan x in this case because I can actually make the full substitution. Remember that what we're going to want to do whenever we do these trig integrals or integrals of this kind is we want to pull out the derivative of one of the functions and then get every term in the integral in terms of that in terms of that particular function. So in this case, we're going to do it for secant. So I'm going to take this, I'm going to make the integral of secant to the 8x tangent squared x times secant x tan x dx. And that's going to then equal the integral, and we're going to have secant to the 8x, and now I'm going to transform tangent x into secant squared x minus 1 times secant x tan x dx. And now everything's in terms of secant x, and I also have the derivatives of secant x, so I can do my U substitution. So this will end up equaling now secant to the 10th x, or the integral of secant 10x minus secant 8x, and all of that multiplied by secant x tan x dx. Now I'll just use my U substitution. I'm going to let U equal secant x, and du is then going to equal secant x tan x dx. So my integral now is u to the 10th minus u to the 8th du, which is a pretty simple integration. It's going to end up being 1 over 11 u to the 11th minus 1 over 9 u to the 9th plus c. When I do my substitution back in, I end up with 1 over 11 secant to the 11th x, minus 1 over 9 secant to the 9th x plus c. So again, this kind of demonstrates the exactly what we want to have happen. What we want to have happen here is we want to actually transform our integral into something that we can then use substitution for. So let's take a look at one more example, and this example is going to be somewhat different because in this case we're not actually looking to do U substitution, but we are going to make a substitution here. The first thing I want to notice is that if I pull out a sine from this integral, from cosine to the 4th x sine squared x dx, that what's going to end up happening is that I'm going to end up with an odd number of sines which I can't substitute in 1 minus cosine squared for. And the same thing is going to be true of pulling out a cosine as well. I'm going to end up with cosine cubed x, which I can't actually make a substitution for either. So consequently, I'm not actually going to do that kind of substitution in this case. Instead, I'm going to use one of those identities that we talked about before. So I know that sine squared x is going to equal 1/2 minus 1/2 cosine 2x. And cosine squared x is going to equal 1/2 plus 1/2 cosine 2x. And so I'm going to utilize those in order to actually make the substitution. So the first thing that I'm going to do is I'm going to let this equal the integral now, and it'll be, I'm going to actually write this whole thing out as 3 terms with our dx, and it'll end up being 1/2 plus 1/2 cosine 2x, 1/2 plus 1/2 cosine 2x, times 1/2 minus 1/2 cosine 2x. And then what I'm going to do is I'm now going to multiply. And the reason why I did it this way is because this is just a difference of squares. So this is going to end up equaling the integral of 1/2 plus 1/2 cosine 2x times 1/4 minus 1/4 cosine squared 2x dx. Then this is going to then equal, and now we'll do the multiplication over again. It's going to be the integral of 1/8 minus 1/8 cosine squared 2x plus 1/8 cosine 2x minus 1/8 cosine cubed 2x dx. So now I've actually got something that I can kind of break apart. If you remember, when we work with integrals, we can actually integrate across addition and subtraction. So what I end up with here is I'm going to end up with the integral of 1/8 dx minus the integral of 1/8 1/8 the integral of cosine squared 2x dx plus 1/8 cosine times the integral of cosine 2x dx minus the integral of 1/8 minus 1/8 cosine cubed 2x. So now we can go in and we can kind of integrate. So I've got 1/8 x, right? That's the first integral, simple one. Then minus 1/8, and what we're going to notice is I again have a cosine squared, although I'm going to have a cosine squared of 2x. And so I'm going to substitute again here for the cosine squared x, but it's now going to be the integral of 1/2 plus 1/2 cosine, and this is going to be 4x, right? Because you're going to double the argument of the function. All that dx plus 1/8, and then cosine 2x, we can actually just use a simple U substitution. It'll end up being 1/2 of sine 2x, and then minus, and then this cosine cubed 2x dx is, we're going to need to utilize our techniques that we learned a little bit earlier. We're going to make that cosine squared 2x cosine x dx. So we've now integrated, these two have been integrated. We now need to finish up the integration on these two functions. So I've got, what I'm going to do is I'm going to do each one of those separately, and then we'll combine everything together. So I'm going to take the integral now of 1/2 plus 1/2 cosine 4x dx, and that's going to end up equaling 1/2 x plus, and this will be 1/2 times 1/4 times sine of 4x, okay, which is just 1/2 x plus 1/8 sine 4x. Then I'll take the integral, and we'll do this last one here. I've got the integral of cosine squared x, or cosine squared 2x cosine 2x dx. Let's change out both of those. Cosine 2x dx. And that'll then give me the integral, and we're going to change this to sine. So this is going to be 1 minus sine squared 2x times cosine 2x dx, which equals, well, what we're going to need now is we're going to use that U substitution. So we're going to let U equal sine 2x dx. And so du is going to equal 2 cosine 2x dx. Excuse me. So the dx is not on the u, it's actually on the du. So this is going to then give me equals 1 minus u squared. We've got to pull over 2, so this is going to be actually 1/2 du equals cosine 2x dx. So we'll come back here. That's going to give me 1/2 times 1/2 du, which is going to equal 1/2 u minus 1/2 times 1/3 u cubed. And when we substitute back in, we get 1/2 sine 2x, right? Because u is sine 2x, minus 1/6 sine cubed 2x. Okay? Now we just need to put it all together. So we're going to go back up to this one here, this equation here. I've got 1/8 x minus 1/8 times 1/2 x plus 1/8 sine 4x plus 1/16 sine 2x minus 1/8 times 1/2 sine 2x minus 1/6 sine cubed 2x plus c. So now finally we're going to get 1/8 x, or well, maybe not finally, actually we've got a little bit more to do. 1/8 x minus 1/16 x minus 1/64 sine 4x plus 1/16 sine 2x minus 1/16 sine 2x. Ooh, that's nice. Minus, plus 1/48 sine cubed 2x plus c. And so when we put everything together, that 1/8 x minus 1/16 x is going to be 1/16 x minus, and let's just do them in terms of powers, minus 1/64 sine to the 4th sine 4x. Sine 4x. These two cancel. They're going to go away. 1/16 sine 2x and minus 1/62 sine 2x plus 1/48 sine cubed 2x plus c. Okay? So, is that involved? Yeah, that's involved. All right? And what we're going to be doing is you're going to be kind of thinking in terms of, you don't want to think about this all, trying to do it all at once. All right? Because it's pretty much impossible. What you want to do is to think, I have some basic tenets, some basic ways of thinking about working with trig integrals. And so I start out, I've got this one where I can't actually pull out a single trig function, right, and then make that transformation. So instead I'm going to have to utilize these, sine squared x, cosine squared x. And you know, in general, that's going to be the case whenever we have two even powers of cosine and sine. Okay, so whenever we have an even powers of cosine and sine, then that's how we're going to have to go. And that might also be when we have like sine of 0x. Okay, that's going to look like that then too. So when we do that, we'll make our substitution, and then it's just a matter of going through and doing that multiplication, doing the simplification. Once we get there, what we're going to do is break that down into some simpler integrals, or integrals that we could actually do something with, and then we've got to utilize our trig, our trig integral methods again. Okay? All right. So what we've got going on here with these trigonometric integrals is we've got some basic, or maybe not basic, but we've got some fundamental identities that we utilize a lot when we're doing trig integrals. And we have that notion that what we're really trying to do is we're trying to do most of the time U substitutions, okay? Or some kind of U substitution, particularly if we have trigs of the right kind. Now, I need to tell you, in addition to what I've shown you here inside of the lecture today, you also want to take a look at your book for some other examples or other instances. So I've given you some kind of canonical examples. They're going to have some instances that we haven't shown here, but they're going to be basically the same, and they're going to be the basically the same ideas. Okay. just writing them all down right now just seems like not a great use of our lecture time. All right. Basic idea here again, right? We're going to pull out one of our trig functions so that we can actually go in and utilize a U substitution, or we're going to make some kind of substitution in order to allow us to create an integral that we can then integrate.